So let's get into problem solving with our two new ideas. And those two new ideas are, once again, that the non-conservative work is equal to the total change in energy, and also that the energy at one point in the system is equal to the energy at another point in the system if and only if the work done by non-conservative forces going from 1 to 2 is equal to 0. And we're going to be able to do a lot of stuff with these two new premises, excuse me. Okay? So before we get too far into this, a couple of other derivations to do, because what we need to do is start establishing, well, what is an equation for gravitational potential energy? So we know, and this is going to seem like I'm backtracking here, that net work is equal to delta KE, right? Good. So these three premises, by the way, are the three foundational premises of this entire unit. We're going to come up with a fourth right now. Well, net work, that's the work done by all forces. That means that net work could be equal to the work done by non-conservative forces plus the work done by conservative forces. Kind of makes sense, yes? And that's going to equal delta KE. Now we know that work done by non-conservative forces is the total change in energy plus the work done by conservative forces is equal to delta KE. Now, go with me here. The total change in energy of the system, that's going to be the change in the kinetic energy plus the change in the potential energies. Okay? Now we know that there should be like summation symbols in front of a lot of these things, but we're kind of like not doing that for the present moment. You notice they have change in kinetic energy on both sides, and there you go. The work done by conservative force is the negative change in the potential energy, and that is our fourth premise, and that's going to enable us to find out equations for potential energies, because all we have to do is calculate the work that they would do going from one position to the other, and that tells us how much the potential energy changed by. So here we go. Gravity. I move an object like that. Here's the force of gravity, moving it up to this location. The work done by gravity is equal to the force of gravity times that displacement, right? Times cosine of the angle. Now, what we discovered here is that this angle here and this displacement, no matter what the path was, what this always resulted in, rather, if this was the displacement, if this weird thing was the displacement, is that always resulted in this coming out to being a change in height. Now we know that the angle here is always going to be obtuse if I'm going upwards. So here we go. The work done by gravity is going to be equal to, well, this is equal to mg, right? This is just going to equal the negative change in the height, right? Because this we said is going to be obtuse, meaning that it's always going to yield some sort of negative number. And we said that the cosine thing, what that does is it gets rid of the side-to-side motion, and we're just left with that change in vertical motion. Therefore, the negative change in gravitational potential energy, because that's gravity is the conservative force, is equal to negative mg delta h. And then getting rid of the deltas, I think we can see that the potential energy to gravity is just mgh, right? It's just about that position, that height, and that's all that matters, okay? Boom, so there we go. So how are we going to use this? Let's do a nice, simple problem. So if I have an object at the top of a hill, and it's gonna go down the hill like this, there we go, right? And I want to know what the speed at the bottom is. So here we go. We're going to use our new ideas in order to do this. So the first thing I'm going to do here is, if you'll notice, potential energy to gravity, mgh, height. Well, what is a height? Well, we generally think of that as the distance from the ground. But that requires a reference. And if you remember back to when we defined potential energy, that was always due to the relative position. So this implies the existence of some h equals 0 point. So let's say that we make the bottom of the hill our h equals 0 point. So now we can say that this object has gravitational potential energy here. When it gets down to the bottom of the hill, it doesn't have gravitational potential energy. Okay, so this is starting to look a little bit easy. Now notice here that hill is curved. Now that's problematic, right? Because if you remember from kinematics, all of our slopes and whatnot, they were all just like absolutely, straight lines, because those straight lines allowed this thing to accelerate at a uniform rate. But this would be a non-uniform rate. But here's the thing, I'm not going to care about that, because all I'm going to care about this position and this position and not the path in between, because conservative forces don't care about the path. Ooh, so that's sort of an interesting thing. This idea of conservative forces and potential energies lets me get away from having to deal with all sorts of curved, weird paths and all sorts of calculus that we said that was going to be problematic at. Anyhow, here we go. Let's say this is position 1 up here, and this is position 2 down here, right? And we know it's going to be moving along here at some sort of V2. We'll say that it has no speed there. It's just like on the precipice. It's about to go over the edge. So up at this location, this object has no kinetic energy because it's not moving, but it does have gravitational potential energy because it's not at h equals 0. This object here at position 2 has kinetic energy because I know it's moving, and it has no gravitational potential energy because it's at h equals 0. Notice there's no thinking about that. That's all observational work. If I look at an object and it is not at the lowest point of the problem where I declared h equals 0, then it has gravitational potential energy. And if I look at the object and it's moving, or I could presume it's moving at that location, it's kinetic energy. So that's a very nice, easy observational piece that we need to do. So now the question becomes, between position 1 and position 2, do any non-conservative forces do work? Well, let's look at the object at some instantaneous position between position 1 and 2. Well, we know the gravity force is acting on it. We know the normal force is acting on it. So the big question is there friction or not? And let's say that this hill is frictionless. Okay, great. So we don't have to worry about friction. But I still ask the question, is there a non-conservative force doing work? Well, the normal force is a non-conservative force, but is it doing work? Well, the answer to that is no, because if I look instantaneously at the velocity vector, it's going to be parallel to the hill, right? Which means that the displacement vector is also instantaneously parallel to the hill, and therefore I know that the normal force is perpendicular to both of those, so the work done by the normal force is equal to 0. So even though there's a non-conservative force acting here, it is not doing any work. So that lets me do something really interesting. Therefore, I can say that the total energy of position 1 is equal to the total energy of position 2 because the work non-conservative between those 2 points is equal to 0. Now notice here, my if and only if became because in this problem, I'm saying it is true. When we were talking about the statement of the idea before, then I didn't have to I didn't know whether it was true or not. I'm saying in the abstract. So in problems, we'll have because as our premise statement. And so what we've been able to do here is say that the potential energy due to gravity at position 1 is equal to the kinetic energy at position 2. And then I know this is mgh1, and this is equal to 1/2 mv2 squared. And if I knew the values of these things, I could plug it in. If I knew the height, I could get the speed. If I knew the speed here, I could get what that height is. Simple enough. Even better, let's look at this position, position 3. This position here is equal to, well, it is above the ground, so I have gravitational potential energy, PEG3, and it's moving here because it's partway down the hill, so it has potential energy. So I could do another little thing here and say, well, the energy of position 1 is equal to the energy of position 3 because the work non-conservative is equal to 0. So once again, that would be potential energy to gravity at 1 here is equal to potential energy to gravity 3 plus kinetic energy at 3, and then plug in mgh1 is equal to mgh3 plus 1/2 mv3 squared. And there you go. If I had the values, I could put it in. Now notice in both of these, the masses would cancel, which is also really interesting. But I'm not going to cancel the masses for my own purposes here, because if I cancel the masses, I wouldn't have like a number for the total energy when I plugged in. And sometimes knowing the total energy of the system is a nice thing. Okay. So let's look at a similar example, the pendulum. Okay, so here's a pendulum, and that pendulum is going back and forth between these 2 points. and I can look at some sort of intermediary phase here. Same thing here. I could draw a line saying that this is where H is equal to 0, right? So therefore, this object here at, say, position 1 has potential energy to gravity position 1. This at 2 has potential energy to gravity 2 plus the kinetic energy at 2. And this has kinetic energy at 3. And then here's the point 4 where it comes instantaneously rest again. And this is potential energy to gravity 4. Some interesting things about this. Once again, let's look at the forces at any given moment. There's the tension, there's the force of gravity. The tension is a non-conservative force. Is it doing work? Well, if we think about it, that tension is always acting radially inwards, and radially inward is perpendicular to anything happening along here, along the path, and therefore the tension is instantaneously perpendicular to the velocity, therefore instantaneously perpendicular to the displacement, and therefore it's not doing any work. So tension is not doing any work here. So we just have the gravity force pulling it back and forth, changing potential energy into kinetic energy and back to potential energy, which is why, by the way, this object gets back up to the same height. If there was no air resistance, there was no friction, that object would swing back and forth, back and forth, back and forth forever. So let's say if I knew there was, 80 joules of energy in the system here, there'd be 80 joules of energy in the system here, there'd be 80 joules of energy which is in this position, and there'd be 80 joules here, distributed somehow between the potential and the kinetic energy based on what the height of position 2 above the ground is. Super simple as a concept, okay? So the conservation of total mechanical energy problems are really straightforward. So what did we do in each case? Well, the first thing that we did in each case is we drew a picture. And just importantly, in this picture, we also identified all key points that we care about. So in this case, the beginning all the way at the bottom, the end here, this intermediate point. The problem will kind of explain to you what the important points are, but generally, start points, end points are key points, identified points in the problem, like it says, maybe it says, after it's gone down a quarter of a meter, what is its speed there? That would be an identified point. We do that. There's a fourth type of point that is important. So we'll get back to that in a second. So we're going to identify all the key points. I labeled them 1, 2, 3, 4. You might go A, B, C, D, whatever. We want to avoid things like initial and final, because if I have more than 2 points in a problem, then the final of one is the initial of another, and that can get very confusing. But we're always going to draw a picture. The next thing we did in this process, 2, is we identified where the potential energy is equal to 0. Now, in the case of gravitational potential energy, that's going to be where the height is equal to 0. We're going to see later on a spring potential energy, and that's going to be at the natural length of the spring. Okay, because that thing has no capacity to affect the environment when it is just at its natural length. Here you go, here's a slinky, no capacity to affect the environment, now it has capacity to affect the environment. There's another video about spring potential energy that we'll go through later, but we're always going to identify where that is true. The next thing we want to do is to write total energy statements for each important point. That's what I did here, right? Now here I probably should have been a little bit more formal, E1, E2, E3, E4, right? Great. Let me see, I did that here in this problem as well, okay? After that, I didn't do a problem here with numbers, but what we'd want to do is write our knowns. And the reason why we do all of this stuff first is because that lets me go back here and say like, okay, well, height 1 is equal to, 4 meters, and velocity 1 is equal to 0. Here, height 2 is equal to 0, and velocity 2 is unknown or something like that. And we write our mass, but I want to know things about like heights and speeds at various points. So it's good to have identified where all those points are with my list of knowns. And I like this like little structure here where I'm writing the total energy statement and then my list of knowns below each of those total energy statement. Here's an optional step, but something to think about is to find the value of the total energy where you can. Okay, so going back to this, pretty obvious here that I could find the total value of that energy if I knew the mass, like it was 10 kilograms or something. I can find the total value of the total energy here because I know the height of 4 meters, 10 kilograms. So 10 kilograms times 9.8 newtons per kilogram times 4 meters, 392 joules, something like that. If I knew the speed here, I could do 1/2 mv squared, find it there, okay? But that's sometimes a very helpful thing to know. And the last thing we're gonna do is we're gonna link our points. And there's two types of links. Either we can identify between 2 points in space that there are no non-conservative forces doing work such that the energy at position 1 is equal to the energy at position 2 because the work non-conservative is equal to 0. Or, between those 2 points, there is non-conservative work. So we'll say that the work done by non-conservative forces is the total change in energy between those 2 points. And that can expand out to be like the energy of the later point. So I will use final here minus the energy initial so that you understand that the time sequence matters here. But I would like put a different, if I had, in this case, that there was friction here, I'd have position 2 minus position 1 or something like that here, okay? And then what we'd be replacing this with is, well, what is the force that's doing non-conservative work, okay? So just to kind of give that example, let's go back to this thing, but let's say that the hill is frictionless, but there's friction here, okay? So here I have position 1 again. Here's position 2 just before it gets to the friction. And then sometime later here, let's say this object stops. So we already did this work from before. So whoops, H equals 0. Here the energy at position 1 is just potential energy to gravity 1. Here the energy at 2 is equal to the kinetic energy at 2. And here the total energy is actually equal to 0 at 3 because there's neither gravitational potential energy, it's at H equals 0. And we said that it comes to rest at some point. Okay, so between these 2 points, the energy at position 1 will equal the energy at position 2 because the work done by non-conservative forces is equal to 0 in this interval. Therefore, the potential energy to gravity at 1 is equal to the kinetic energy at 2, and then I can do all sorts of things there. But between these 2 points, the work done by non-conservative forces is equal to the total change in energy. Here, there are 2 non-conservative forces acting. The normal force while I'm here, right? So let's boom and boom. And there's our frictional force, and the frictional force is acting, and this is equal to the energy at 3 minus the energy at 2. Now I know the work done by the normal force is 0, because the angle between the normal force and the instantaneous displacement, which is like this, is equal to 90, right? So I just get the work done by friction is equal to the energy at 3 minus the energy at 2, and so then that becomes the work done by friction is the force of friction times the displacement between 2 to 3 times the cosine of theta k is equal to energy at 3 is 0 minus, and then this is just the kinetic energy at position 2, right? I'd have to find the kinetic friction, which means I'd have to find the normal force. I would have to actually do a force problem here. Sum of forces in this section is equal to MAY, right? And so Fn minus Fg is equal to MAY. We never just assume that's going to be true. We always prove it. Fn is equal to mg in this case, right? If I was on the hill, it would not. It would be equal to the y component, right? If there's an angled force, these would not be equal. So we just have to prove it every single time. So that means if the work done by non-conservative forces is not 0, and I have to do a work problem, then I have to do a free body diagram for the object in the interval where that non-conservative force is doing work, so I can find out what the friction force is, because I'm going to need the normal force, okay? But here's how you can see how those links happen. And so that's really what the problems are. It's about identifying the forces, or identifying the points, and then identifying what type of energy it has all the different points by observation, and then linking them by asking the question, does non-conservative forces do work in this interval, or do they not? And then go one of these 2 routes. And that's pretty much every single problem, okay? So you'll see some problems with this, and then we'll add springs onto this, and then the unit's done. So there we go.